Today we're going to be working on an optimization problem. Now, optimization problems are actually very useful in real life and kind of everyday usage. So the problem that we're going to do today is going to be utilizing some kind of everyday needs. So we have two sisters who have enough money to buy 100 feet of materials to build out their bedrooms. Now, the bedrooms have to be in the same place and they have to be next to each other. But as they are sisters, they want to make sure that they each have enough space in their rooms to help build it out. Now, some of the things that we know is that there is a 6-foot closet on one wall, a 3-foot closet on another wall, and of course separate entrances for both of the sisters, which are both 3 feet each. Now, because one sister does not want only a 3-foot closet when her sister gets a 6-foot closet, they're going to split this closet up. So we have to have one wall in the middle in order to give them optimization of the inside area. So we're going to start out with the area of a rectangle, which is length times width. Now, this will be our x-axis, and these will be our y-axes. And this is also an x-axis as well. So we have 3 y-axes, 1, 2, and 3, and 2 x-axes, 1 and 2. Now you notice that we have all these holes here, so we do have to do some accounting for that, and that's where our negative 15 comes in. So we have 3y plus 2x minus 15 equals our 100. Now, because we have two different variables, we have to get these all equal to one sign because we can't have both an x and a y in our problem. So what we want to do is we want to shift our variables around so that we can get either a y answer or an x answer. So I'm going to choose the y answer today in order to give us an equation that we can work with. So we're going to do y is equal to 115 minus 2x all over 3. All right? So if you see how I did that, I just added the 15 to this side, making this 115, and I moved the 2x to this side, making it a negative 2x, and then I divided 3 by both sides, leaving my y by itself and putting my 3 over here as the denominator. So now we have our problem solved for y, and so we can go back and say, okay, let's plug this in to our area. So remember up here we had area equals length times width, so basically x times y. So we're going to do area, and then we're going to plug in the equation that we just got, which is 115 minus 2x all over 3 with that whole thing multiplied by x. Here, I'm going to put another parentheses there so we can see what's going on here. Multiplied by x. All right? So what that gives us, of course, is a equals 115x, x minus 2x to the square root of 2 all over 3. All over 3. Okay, put some parentheses in there just so that we can see that. All right, so this is what we have so far. So we have our area is equal to 115x minus 2x squared all divided by 3. So that's getting us close. So now what needs to happen is that we actually need to take the derivative of this equation right here in order to move forward and be able to find our maximum. So I'm just going to kind of get rid of this. Well, let me put this up just a little bit, maybe make these guys a little bit smaller so that we have room, oh dear, to do what needs to be done. So hold on, didn't quite get that right. So let me just move these guys up here so we can see them. And then we're going to go ahead and take the derivative of our area. So we're going to do a prime. And of course, taking the derivative of 115x is just equal to 115. And then taking the derivative of negative 2x squared is negative 4x. And this is all over 3. All right, let's put my parentheses back over here. All right, so now we have the derivative of our equation. We say, okay, well, that's all well and good, but now we need to find our critical values. And so in order to do that, we're going to want to set our derivative equal to 0. So we're going to plug a 0 in right there and set our equation equal to that. All right. So we know that in order to get a critical value, only our numerator is what's important. So, we can try to get our x and get it equal to this. Well, doing some basic arithmetic, we're going to get our x equal to, and this is a pretty big number, but we're going to go ahead. It's 115. Well, it's actually negative 115 divided by negative 4, which is going to give us an approximate answer of 28.8. Okay, so our x value's approximation is 28.8. Right? So that gets us pretty far into this problem. But this does not prove that we're at our optimal value, because 28.8 is where we think might be the maximum, but now we have to actually prove that, because if we don't prove that this is the best answer for x, then we're just building without a really good plan. So we're going to create a number line in order to give ourselves a bit of a visual for proving this, okay? So what we're going to do is we're going to say, okay, well, 28.8 is our value. And so we want to put that value in line and choose some test values to go along with it. So since our critical point value is 28, I think I'm just going to choose 20 as one test value. And then I'm going to put my 28.8 here. And then my last value I'm going to put as 40. These are some pretty big numbers here. So let me see if I'm going to move this over a little bit. All right, so knowing that this is our critical value and these are our test values, so we want to see how these values test in our derivative to see if this truly is the best maximum. All right, so what we're going to do is we're going to plug 20 into our x value here and see what happens. So here we go. So if we plug 20 into our x value here, that's going to give us 80. So 115 minus 80 is still a positive number. Divided by 3 is still a positive number. So we can see that this is positive, right? And then when we want to plug in 40 into this number, that would be 4 times 40, which is 160. So 115 minus 160 is a negative, divided by 3 is still a negative. Oops, I didn't know that wasn't there. There we go, got that there. So that's still a negative. So on one side we have a positive, and on the other side we have a negative. And so what that would look like would be an arrow. So we got an arrow over here, we don't. What that would look like is an arrow going up in this direction. So we have the function going up. And then on the other side we have it going down. So that means that 28.8 really is our maximum. And so we can say that the area is maximized when the length of the room is 28.8 feet. So that's the area that gets maximized. And of course then we can go back in and plug in this value into our x value here and get our y value, which happens to be 19.1. And then when we factor out this incomplete equation, then we have an understanding that each of our x values are 28.8, each of our y values is 19.1, and we subtract off our doors, and we have the optimal value for maximizing area of our 2 girls' rooms. So go ahead and practice a few more practice problems from your book, and just make sure that you're doing proper accounting and that you're taking you're starting with the correct equation, and then making sure that you have accounted for all the x's and all the y's and anything that might be missing from there, and then going down and getting your derivative from your area equation. And then once you get down to your x value, that you test your x value, because this number means nothing if we don't test it and see, yeah, this actually is a maximum right here, because we have a positive on one side and the negative on the other. So we know that it is actually changing directions at that point. So I hope this was helpful to you, and if you have any questions, please feel free to let me know.